So I have been explaining how logistic regression works in this very simple example where we've got recall accuracies in an experiment where we're increasing the set size, the number of words that a participant has to see and then recall one of them, right? And so we are at the point where we can now fit the model because we decided on some priors. And as I mentioned earlier, we are not committed to using only one set of priors. A sensitivity analysis consists of changing the priors to see what the posterior distribution looks like. So when I publish papers, I will sometimes show posterior distributions under a range of different prior assumptions. And so that's a very useful thing to do, and you should not limit yourself to any one prior. So, but in this example, I'm limiting myself to this one prior because time is limited. So I want to get to the point quickly, right? So I've chosen one prior for the intercept, and I've chosen another prior for the slope here, right? And these are the only parameters in this simple model. It's a simple logistic regression model, not correct for these data, because they're not independent, but we are assuming that they are, right, just for illustration. So these are 0-1 responses. So as you notice here in the software, what goes into the model is the 0-1 responses. This is very counterintuitive because the model itself is working with the theta probabilities, right? So that's something you have to stay aware of, that even though we are writing out this linear model with 0-1 as our dependent variable, underlyingly we are modeling log odds, right, with the intercept and slope. So here's my data. Now notice I've got a new family of functions defined here. Until now we had only seen the normal and the log normal. Now we have the Bernoulli, and now you know why, right? Because we are assuming a Bernoulli likelihood, and we are assuming the logit link function, which I explained earlier, okay? The prior specifications I've already discussed, and so now we are in a very good position once we fit this model to look at the posterior summary and to interpret the results, okay? So let's do that graphically, right? I always find it easier to understand the posteriors graphically rather than trying to look at the numbers. And so again, the fat hairy caterpillars are looking good, so I don't have to worry so much about the convergence problems here, any convergence problems here. The intercept is showing me the average, grand average accuracy in log odd space, right? And the slope is giving me the effect of increasing set size from 0 to 1, right, on accuracy in log odd space, okay? So again, this is hard to interpret. I do see, though, that these numbers are negative, right? The fact that these numbers are negative tells me that increasing set size is going to reduce the log odds of getting a correct answer, right? Therefore, the probability is going to go down as expected, right? So it's not a surprise here, okay? That's a good thing. I mean, it would be very surprising if your accuracy starts going up with the increasing set size, right? So then there could be something wrong in your data set, for example, right? Seems highly implausible. Again, as before, we are in the log odd space. We don't know how to interpret it because we are human beings. We would interpret everything in the probability space, but we can back transform. We know how to do that. First, I extract the alpha samples, the intercept samples from the posterior distribution from the fitted model. I extract the samples for the intercept, extract the samples for the slope, and then I'm ready to go. So how do I do this? If I want to figure out the mean of the beta samples, that's easy to do, right? With these built-in functions, you can also figure out the lower and upper quantiles of the beta samples and then summarize those, for example. And you can also do this for accuracy, right? So you can do this on the probability scale. The way you would do this is by using that function that I showed you earlier, right? So you're basically converting back from log odd space to the probability space. That's that p-logis function. So this is giving me average accuracy. This is a really amazing thing, actually. What I'm getting back is the distribution of the average accuracy, the posterior distribution in the probability scale. So now I can directly interpret my uncertainty about the average accuracy on the probability scale, having fit the model on log odd scale, right? And so what I get is that the average accuracy is about 87%, with a 95% credible interval going from 80 to 93%. Right? So what that tells me is that I'm pretty sure, given these data, of course, I don't know if this is the truth, right? I just know what I have from the data, that the range of accuracies in this data set is 80 to 93%, given my prior on the alpha parameter and given the model that I have and the data, of course, right? Okay. So another thing that you can figure out, which is extremely useful now, is the decrease in accuracy in the probability scale, right? That's a super useful thing to do. And so that's something that I've done here. And what I've done here is that I've converted everything back to probability space using the p-logis function. And what you're seeing is the decrease in accuracy here on the probability scale when you decrease the set size by 1 unit. Oh, sorry, you increase the set size by 1 unit, right? So when you increase the set size, then the accuracy will go down, right? So that's what this is showing you now. Okay, you can also compute, in the experiment we had set size 2, set size 4, set size 6, set size 8. So you could ask questions like, what is the change in accuracy when you go from set size 2 to 4? Or 4 to 6, or 6 to 8, right? All that can be now computed because all I need is the alpha samples, the beta samples, right? And I need to just plug in the particular differences that I'm interested in, right? The particular values for set size that I'm interested in, centered, of course, right? And then I can just compute the probabilities. So this is the change in probability as I go from set size to 2 to 4, for example, right? That's a very useful quantity to know now. Okay, so you can see that one could look at the data from many different angles now and interpret many interesting details there. And there's more about this in the textbook, of course. I just gave you a brief overview of how to fit simple linear models. And I showed you how to fit a model with a predictor. And what I didn't show is that you could have more than one predictor. That, of course, is now completely general. You can keep adding more predictors. There are, of course, complications associated with that, but that's a secondary issue that I will not talk about right now. What I do want to talk about next is this very important topic of hierarchical models. This is where the real amazingness of the Bayesian framework comes into play, right? So it's a very, very powerful approach to modeling data with repeated measurements, which is the kind of data we are working with. Until now, we've been ignoring the repeated measures nature of the data, but now we are going to start paying attention to it. And for that, we need something called hierarchical models, and that's what I will quickly introduce to you very briefly. I won't discuss too many details. This is all in chapter 5, so you can look at that once the course is over if you want to use these in your research.